So we're doing some practice problems. The derivative here is a chain rule. So the derivative of the outside function cosecant is negative cosecant cotangent. Leave the inside function alone, times the derivative of the inside function, x cubed, which is 3x squared. And we'll bring the 3x to the front, so we'll write it as negative 3x squared cosecant of x squared cotangent, or cosecant of x cubed, I guess, and cotangent of x cubed. Okay, so let's try another one. Let's do, let's choose y equals the logarithm base 5 of the absolute value of 2x over 1 plus cosine x. Remember how to do this, or you need a suggestion or a start? So remember, a logarithm is not a base Euler's number. It's not a natural logarithm. We want to convert it to a natural logarithm by doing change of base. And change of base means we're going to take the natural log of this and divide it by the natural log of the old base that we're getting rid of. So it's going to be natural log of this over natural log 5. You can think of pulling that 1 over natural log 5 out as a constant. Then it might be a good idea to use your property of logarithms on the division and split that into 2 separate logarithms, and then take their derivatives, and then bring back the 1 over natural log 5. Should have volunteered for the first one. Let's get some volunteers up here. And you can consult and collaborate. So when we have a logarithm that's not base Euler's number, it's not a natural logarithm. Before we take a derivative, we're going to do a change of base. So essentially what we do is make it into the natural log that we want. And then as a price, we have to throw in this extra constant, the natural log of the old base 5. Then what I would do, or this is the way I think of it, and I'm not going to do any calculus yet. So I would just kind of pull out that constant, because it just kind of gets in the way, and it's easy to confuse and think you have to do something with it, like a product rule or a quotient rule or something, and you don't, because it's just a constant. It just hangs out. Now this logarithm, I wouldn't jump into differentiating right away, because then that becomes a complicated quotient rule, chain rule, all that kind of stuff thrown in once. Instead, use your property of logarithms and separate that out into the difference of the 2 logs. Then you can, now this one isn't a big deal because this is not a hard chain rule derivative, but you could further break that down and say that's the natural log of 2 plus the natural log of x minus the natural log of 1 plus cosine x to there. But that's an optional step there. Now when you go to differentiate it, so this is still a y, and our derivative, the constant just hangs out. So you don't have to do anything with that at all. This is a constant, so its derivative is 0. The derivative of natural log x is 1 over x. Now, you don't have to worry either about the absolute values. The absolute value in the logarithm extends the domain. Because remember, a normal logarithm, without an absolute value, if you think about that graph, it's only defined for x greater than 0. When we take its derivative, we get 1 over x, but 1 over x is defined for negatives. So without the absolute value, you don't gain this. You can't gain domain through differentiation. You just get 1 over x, but it's got the restricted domain that x is only good for positives. when you put in the absolute value, now you extend the domain of the natural logarithm so that it matches the domain of 1 over x. Because now we can put in negatives because the absolute value will make it a positive, and then it's defined in the logarithm function. And then its derivative really does match. So your original function and your derivative have the same domain, which is true here too, but it's a restricted domain. You don't get that when you have just the natural log of x. So the takeaway is the absolute value of x extends the domain of the logarithm. When you differentiate it, the absolute values just go away. They aren't there anymore. And if you try to put them in there, it's wrong. So don't. Okay? And then here, now we have a chain rule derivative, which remember is going to be 1 over u du, or you can think of it as du over u, either way. So it's going to be, it's a minus originally. 1 over u is going to be 1 over 1 plus cosine x. Times du, the derivative of cosine is a negative sign, which makes that into a plus. So if you're fine to leave it like this, that's okay. If you want to distribute, you can as well. It's going to look messy no matter what you do with it, because you're going to have that natural log 5 hanging around, which is kind of annoying, which is why natural logarithms are so much preferred over a logarithm any other base. So you don't have to deal with that. Does that make sense? Okay, let's do another one. And if you haven't been to the board yet, you have volunteered to do this one. Thank you for your service. Okay, so here we have a quotient rule. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. And so this cancels and becomes 1, and there's our derivative. Crazy. Let's try another one. Okay. We have to remind you of how this one works. We see these rarely, and so it's hard to remember what our strategy is. We have y equals the cosine of x to the sine of x powered. How in the world are we going to do this? Do we have any suggestions? It is not a power rule, so you can't bring the exponent out in front times the function to the exponent minus 1. It is not an exponential, where you have a number to a function, or you can get that number, the same exponential back, times the derivative of the exponent, times natural log of the base. It takes a special technique known as, there's a chain rule going to come up, but it's logarithmic differentiation. So we're going to take the natural log of both sides. You with me? Then we're going to use our property of logarithms to bring that in front. It's going to become a product rule on the right side, and we're going to have to do implicit differentiation with the natural log of y on this side. Remember, you're ultimately trying to solve for y prime. I don't want to take away all the fun. Come to the board and give it a chance. You get stuck, let me know. I'll help you. So this requires what's called logarithmic differentiation. When you have a function raised to a function. So it doesn't follow the power rule. It doesn't follow the derivative of exponentials like e to the x or 5 to the x rule. So there is no rule for it. So we are going to take the natural log of both sides That will let us use our property of logarithms to get that function out of the exponent and make it into just an ordinary multiplication. Now our y is buried in this logarithm, so when we differentiate, we're going to have to do that implicit differentiation here. So we're going to get 1 over u times du. And the derivative of y we're going to call y prime. We're going to solve for that. So, but over here, now we have our product rule. So we have the first times the derivative of natural log of u, which is 1 over u du. That's going to lead to a negative sine x over cosine x. Plus the second, that natural log of cosine of x, times the derivative of the first, the sine x, which is cosine x. But I don't want it to look like it's in the logarithm. So I'm going to write it this way. Now we're going to multiply the y to the other side. We know, and I would call the sine over cosine the negative tangent. And so call that negative sine x tangent x. Although you could call it sine squared over cosine. And there's not really a great way of writing that, but we're going to leave it like that. And the final answer is we're not going to leave the y in there because we know that the original y was cosine x to the sine x. So our derivative at the end of the day is going to be this cosine x raised to the sine x times this mess, which there's not a whole lot else we can do with it. That's implicit differentiation. It's what's called logarithmic differentiation. I'm sorry, it's logarithmic differentiation. Okay? All right. Let's pause here and see if there's any questions on the homeworks. When you would like to see clarified.
Can you do 17 from homework 37?
Do you know what that is? We're going to use Brian's book.
It's the, I don't know what it is, but it's the one from the Larson's worksheet. It's the homework before this one.
Okay, does anybody have that handy or, oh, Priya, you're a saint. Otherwise, I can pull it up on Canvas, but.
Okay, so it's the graph one. It's f of x is x, and g of x is tangent x.
We were talking about this morning, right? And we want to find where they intersect, is that right?
Yeah, and h of x is f of x minus.
And then, so you got the tangent x. And do they give us a domain where they want that?
It's pi over 2 and then 3 pi over 2.
Okay. So tangent is this periodic function. So the tangent has asymptotes at the over 2's. It's going to look something like that. And y equals x we know is just a, oops, I missed the y-axis there. So it's going to be just this 45-degree angle line. We're trying to figure out where they intersect, but we want to use Newton's method to do it. So Newton's method, remember, finds zeros of functions. It doesn't find intersections per se. So we want to change our intersection question, you know, where we want to know where is f equal to g, into a new function, so we can subtract one from the other, so that finding the zero of this one function is finding where these two functions intersect each other. Does that make sense? Now, the tricky part, so this is what you're going to use as your h. You're going to have to find h prime. And so that's going to be 1 minus, and the derivative of tangent is secant squared. So here's your derivative, and your original function is that x minus tangent x. So we're gonna try to put, this in as y1, this in as y2. We're gonna do that magical stuff we do on the calculator using this Newton's method to approximate the zeros. But it's really tricky because of this asymptote here. You can see that this is going to, that these are going to intersect somewhere close to 3 pi over 2. But because this is also pretty close to that vertical asymptote, if you don't get the right first guess, you aren't going to get a value that's in between pi over 2 and 3 pi over 2. And so that, because they're going to be, this tangent is infinite. So it's going on and on and on in both directions. So is y over x. So you're going to get an intersection in each of these regions between and over 2. So there's going to be an intersection between these two at 0, between negative pi over 2 and pi over 2. The one we want is between pi over 2 and 3 pi over 2. But there's going to be more intersections as you go. There's an infinite number of intersections. So to get the one that you want, you have to be really careful about what you choose. And so it may take some trial and error. And I don't remember exactly what it is. But I do know you got to be pretty close or it's going to send you off into the hinterlands. Is that enough to get you going? So a little trial and error there. And if all else fails, you can go see what the answer is, or find the answer using your zero finding capabilities of this, and then make your guess pretty close to that. What else? Yeah.
Could you please do number 12 on homework, or 11, sorry, on homework 38?
11, do you know what that is?
Yes, sir. There's a figure in it, though.
What's that?
There's a figure in it, though.
Okay, so we do look at that. What, you know, page we're on?
Yes, sir. 178.
178. Okay. This is on page 178, and we have find the mean value theorem with a equals 3, b equals 13. A equals 3, b equals 13. Choose a function given in our figure leads to the point C shown below. And what is the value of f prime of C? What can we say about the values of f prime of x1 and x2? So you're given a curve that looks something like that. You got a point at 312 right here. And we got a point over here at 13.7. And give us a couple other points along the way. So there's our x1, one of our mystery points. Here's our x2. And this is our point C. Okay. So if you remember what the mean value theorem says is when we have a continuous and differentiable function, which we do because you can see it's all connected and there's no corner points or cusps or anything weird happening there, then the mean value theorem says that f prime of C is f of b minus f of a over b minus a, somewhere on that interval. So they're telling us then that here's the a and here's the b. So we know that f prime of C is going to be b, 7 minus 12. So b, I'm subtracting the f of b minus f of a, those are the y values. And then we're going to subtract the x values. Is that okay? And so 7 minus 12 is negative 5. 13 minus 3 is 10. So that looks like negative a half. So the first part of the question was, I think they asked what was f prime of C. Yeah, what is the value of f prime of C? And we have found that. F prime of C is a negative 1/2. Then they want to know, what can we say about f prime of x of 1 and f prime of x of 2? So I think what we can say is that, we can see that this slope of the line joining those 2 points is that negative 1/2, which is the same as the slope of the tangent line at C. So if we want to compare and contrast that to the slope of the tangent line at x1, and I'm going to pick a different color than that, and the slope of the tangent line at x of 2, what could we say? Now remember, these are negative slopes. So, if this was, say, a negative 1, this is flatter, so it might be, or actually, this is negative 1/2, because that's what we said it was. Then this would have to be still negative, but it's going to be closer to 0 than negative 1/2, which makes it actually bigger. So you're going to say that a prime of x of 1 is going to be bigger than negative 1/2. A prime of x of 1 is bigger than negative 1/2, but it's also going to be negative, right? You can see that. So if we write that maybe in a more logical way from small to big, our derivative of x of 1 is going to be in between negative 1/2 and 0. Does that make sense? And about all we can say about x of 2 is, that's a steeper negative slope, which is going to make it a smaller number. A bigger negative number, which makes it smaller compared to the negative 1/2. So I think the best we can say for f prime of x of 2 is it's going to be less than a negative 1/2. Does that make sense?
Yes, sir.
Tough question. That's a good one. What else?
We did 14 on that same page.
14 on the same page. Use the racetrack principle, which we didn't really get a chance to talk about much, and the fact that sine of 0 is 0 to show that sine x is less than or equal to x for all x greater than or equal to 0. So, okay, so we've got, this is 14. So sine of 0 is 0, and sine of 0 equals 0. And we're going to compare sine x to x. And we want to show that sine of x is less than or equal to x for all x greater than or equal to 0. Okay. So the idea is we're going to compare these two. And if we look at their derivatives, so if I just, to make this a little easier, I'm going to call this one f and this one g. So if we look at f prime of x, so f prime of x is going to be the derivative of sine, which is cosine, and g prime of x is going to be 1. So we can see that the derivative of sine of x, the biggest cosine can ever be is 1. So it's going to always be less than or equal to g prime of x. So that's talking rate of change. So we're saying that the rate of change of x is always going to be greater than or equal to the rate of change of sine of x. If they start at the same place, and this one is always growing at least as fast as this one, then this function must always be greater than or equal to that function. Let me say that again. So that means that g of x must always be greater than or equal to sine of x. which you can kind of see. I mean, if you look at the graph, it's pretty clear. Because if you look at y equals x, it's going to look something like that. And sine of x is going to, it's kind of hard to tell what's going on there, but it actually does, you know, I mean, once you get very far along the way, it's pretty clear that y equals x is always above the sine curve. So it's always greater than or equal to the sine curve. But this is saying that even in here, it's not real clear the way I drew it. But in fact, this line is always greater than or equal to the sine curve. Sine curve doesn't somehow come up above here at all. You don't look convinced?
No, that makes sense.
It does make sense? Okay, good. I'm going to paint myself in a corner otherwise, and then I get in a jam. Okay, that's what our book calls the racetrack principle. If you know that one has a derivative greater than or equal to the other, and they start in the same place, the one that's growing faster has to be bigger than or equal to this other one all the way through. If they end at the same place, then the one that's growing faster must have been catching up all the time. And it finally caught its right at the end. So you can use the racetrack principle kind of on either end of that. What else? Well, let's practice some more. I can do this all day. Let's see. Let's say that. Let's write in algebraic form. I don't want you to take a derivative or anything like that, but I want you to find, let's say, find the cosecant of the arctangent of 3x. What in the world does that mean? I don't know, but hopefully somebody in that next group that's supposed to be up here can figure it out. Any suggestions? None. So remember, this is an angle whose tangent is 3x. So you're going to draw an angle in quadrant 1, label its sides so that its tangent is 3x. Use a little Pythagorean theorem to find your missing side. Then take the cosecant of that angle. What? Does that make sense? No? Okay, I'll do this one with you. Don't think you're off the hook. So, an arctangent is an angle. So I'm going to draw an angle. There's my arctangent. It's the angle whose tangent is x. And from SOHCAHTOA, we know that tangent is opposite over adjacent. So the tangent must be 3x. Well, that must be 3x over 1. Now we can do some Pythagorean theorem to find the hypotenuse. Let's see. A squared plus b squared equals c squared. Remember, you're squaring the quantity 3x. So that's 1 plus 9x squared. Okay? So c is going to be the square root of that. Is that 1 plus 3x?
No.
Good. Even if you thought it was, don't. No. Okay? Now there's our angle. Now we're going to take the cosecant of that angle. Well, let's see, we know sine is opposite over hypotenuse. Cosecant is the reciprocal, so it's going to be hypotenuse over opposite. That's going to be hypotenuse over opposite. Got it. No calculus. We're going to take a derivative. Not to say that it's easy. Okay, now let's see what you can do. Write in algebraic form. And let's do the tangent of the arc cosine of x give it a shot. Oh, I forgot to play the video. I'm gonna redo this last one for the video. So just ignore me for a moment. I know I don't have to tell Katie that twice. What did I say that was? Cosine of what? 3x was it? So cosecant of arctangent?
Yeah.
Cosecant of arctangent of 3x?
I can.
Oh, we did do that one. Let's see what we can do. So here's our triangle. We knew that the cosine was x over x plus 2. So a little Pythagorean theorem to try to figure out what the b is, what this opposite side is. So I think if we square that out, we get x squared plus 4x plus 4. If we subtract the x squared, we just get 4x plus 4. Square root, who could pass up the opportunity to recognize that as 4 times square root of x plus 1. Square root of 4 comes outside the radical as 2 times the square root of x plus 1. So we could call that opposite side there. Now the tangent is going to be the opposite over adjacent. So that is going to be there. Is that okay? Okay, so let's try another, but let's do a challenging derivative. So we have y equals arc sine of the square root of 1 minus 49x squared, and we are going to try to find the derivative. Now this is a tough chain rule derivative there. See what you can do with that. I'm going to deal you out a review here. I'm going to get us started here. You keep working there. I'm going to get us started there. So we want the derivative of arc sine of u is du over the square root of 1 minus u squared. The du is a big chain rule derivative. So it's 1/2 times the inside function to the negative 1/2 times the derivative of the inside function. All that's just the du. Then we have the square root of 1 minus u squared. Now a little cleanup here. The 1/2 will cancel with negative 98x, so that's going to be a negative 49x. So that's going to be a negative 49x. That's going to still be in the numerator. This is going to move into the denominator as the square root of 1 minus 49x squared. Meanwhile, inside that radical, we square that, which gets rid of the radical. But remember that minus u squared, that minus has to distribute. So it's going to get rid of the 1, and it's going to make that be a positive square root of 49x squared. Now is where you're in dangerous territory. So the square root of 49 is 7. The square root of x squared is not x, the absolute value of x. Because it has to be non-negative. The 7 can cancel with the negative 49, but the x cannot cancel with the absolute value because they are not the same for all values of x. So we are trying to get to negative 7x over the absolute value of x times the square root of 1 minus 49x squared. Ooh, that is a problem.